Hello and welcome to the projected chopper task. Here we are finally talking about the projections. So in the previous task we saw the projection matrix. What does it do? It has this frustum, right? And here we are finally dealing with this. So in this task we will use both projections to see the chopper or tetrahedron in many different perspectives. So for example, you can see here the main view is with the perspective camera, and then in the corner we have an orthographic projection view in a small sub window. And yeah, we are using the perspective projection and the orthographic camera in this task. But what is this orthographic camera? What what does it look like? What's the intuition behind this? So we can see that with the perspective camera, the viewer is a point, like, and this is the screen here, the screen. But with the orthographic camera, the viewer is a plane. So this plane here is a viewer, and this here is the frustum. And that means that if we have this cube, or a cuboid rather, and we have the viewing plane, so this is the viewing plane of the orthographic projection, then what we do is we just project everything perpendicular to the plane onto the plane, and this cube would look like a square. Like, this cube actually would look like a square in perspective as well, but for example, if we translate the cube downwards, we would see over the cube, and we would see the top face when we would use perspective. But with projected, with the orthographic projection, we see no difference. We just see the front face when the front face is perpendicular to the viewing plane. It also doesn't matter how far the viewing plane is. So this plane might be like millions of units away, or even closer or further away, it would look exactly the same, because like it's perpendicular, so there is no there's no deformation, or so that's the orthographic camera. It's a bit different to the perspective camera, but this is very useful, and we'll see the difference in this task as well. And yeah, we have to create 3 different orthographic views. So one is from the front of the chopper, the another is from the top of the chopper, and the third one is from the side of the chopper. So from x-axis, from y-axis, and from z-axis. And yeah, we will use the GL viewport and GL scissor functions this time. This will allow us to create 2 viewports in one screen at the same time. If you download the code, you can see that this will look very similar to the previous task. And indeed, you should take your chopper code and add this to this code as well. But if you don't have a chopper right now, there is a replacement tetrahedron right now. So this colorful tetrahedron, we can still do the tasks with this tetrahedron, but you should add your gradiented chopper here. If you look more closely to the code as well, you can see that we still have grid wall, but now we also have the change secondary camera mode. So we have a primary and secondary camera. The primary camera is the one for the perspective camera, and the secondary camera is for the orthographic projection. Yeah, we also have the tetrahedron vertex array object as well here for testing. If you have a chopper already, then you can remove this. We also have some information about the camera. We also have screen width and height. This will be useful. They have to be in the variables because we will start using them. But we also have a field of view, and this perspective view here. This depends on the field of view, and we want to change the field of view with arrow keys. And we can see what happens if we change the field of view. When we make it very narrow or very wide. And also we have this question, what happens if the field of view is too big or too small, less than 0 or more than 180? You have to explain why that is. Okay, we've added this structure here called camera. This is a convenient structure that just holds the view matrix and projection matrix in one container. And this is useful because usually the camera is defined by those two things. So the view matrix is the position and orientation of the camera, and the projection is if we have the orthographic projection or the perspective projection. So those two things make up a camera structure. Then the init chopper you have to fill, and you also fill the create cube and the draw chopper. Then if we scroll down, we see that the first thing that we had to implement is the key left and key right handlers. So previously we've had only this thing here, which just handles the closing of the window. But now we want to also detect the arrow keys that go left and right, so to change the field of view. So what we have to do is change the global field of view. We just saw that field of view global variable. Then we create a new perspective matrix from that field of view and assign it to the main camera projection. So we have main camera. We also have secondary camera here as well. So we have two cameras here, the main camera and we have secondary camera. And here as well, so for left should decrease and right should increase, or another way around. Then there is a function change secondary camera modes. So we saw that we have these three different possibilities. So this should change the secondary camera mode from front view to the top view, or from top view to the side view. And yeah, modes are 1, 2, 3, and then they will have to start like rotating every 2 seconds or something. And currently only one mode is defined, just mode 1. So it's the position at 15. We look at the 0, and the up is y up. So you want to ask a question, what is up vector? We will look at it at the lecture as well, but I will just give a brief overview on the whiteboard as well. So if we have a chopper, for example, this small chopper here, and we have wings as well, then we want to render this chopper, so we put the camera in our world as well. So now we have a camera, this is this, but now the question, now there's a question, how is this camera oriented? So we know that it looks in the direction of the chopper, which is defined by the look at camera. We know the position, which is the first argument of our look at function. But now the up vector, what is it useful for? So the thing is that this roll here, like how is this camera rotated, this is still hanging. Like we do not know what the role should be. And the up vector is just one vector that removes the ambiguity. And exactly the same, we have another camera looking from this place, but we put the up vector like this. Now the role is still ambiguous, so not all the up vectors are valid. In fact, this might crash the program because there might be division by 0 here. So the up vector cannot be collinear with the look at vector. If they are not collinear, then the up vector will define the role of the camera. And what we want to do is so that the camera role is such that the plates are above the body. Like if we saw just like we saw in the task description. So here we have to just change the position. Look at might stay same because we want to see the chopper, and the chopper should be at the 0, 0, 0, but up will change according to the position of the camera. So that's what we have to do here. And then finally, there is this good command block here, and this is the final thing we had to do. So here we handle the two viewports. So for example, if I activate it right now, you can see that we have this hanger and we have the tetrahedron. We can actually see if the secondary camera works if we change the projection and view matrices here. We can see now that the walls are not visible because they are perpendicular. We can see that only the back wall of the hanger is visible. This means that the frustum is smaller than the hanger itself. You can also see that the tetrahedron rotates a bit differently than perspective camera with the perspective camera. And yeah, so one thing you can also notice is that the tetrahedron is stretched out a bit. This is because the frustum of the orthographic camera currently assumes that the viewport is a square, but our viewport is not a square. It's wider than taller. But we can change it back, and yeah, we can now actually start doing this. So we want to do the same thing here, but for the not here. We want to do the same thing here, but for the smaller viewport as well. So let's clear the color. We put the new cameras here as well, so secondary camera. So now we are doing the same thing as with the first camera, but for the secondary camera as well. And we want this to be in a corner, so we'll use the GL viewport function to do that. So we have to do it before we draw. And if I go to the documentation, let's see what it takes in. So it takes in X and Y coordinates and width and height. So for now, we'll just set it to 0, 0 and 150, 150. And if we run it now, there should be a smaller orthographic view as well. But now we see the problem that the big one, the default one, this is overwritten. And one might think that this clear here is the problem, but if I remove it and run it again, it's still the problem. So now we have to use the GL scissor function as well. And if we put the scissor here, this scissor tells that do not change anything other than this area. So the clear should be fine. But if we run it now, we see that it's flickering. And this is the problem because we need to also set the viewport and scissor sizes for the default camera as well. So let's copy this and put it here. So the positions can be same, but now we need to use the screen width for the x-axis and screen height for the y-axis. And now it should work for both of them. Yeah, and we can see we have a perspective camera view here with the big screen, and then at the corner we have this orthographic view as well. And since the orthographic view is now square, the tetrahedron is not stretched out. And what one thing you also have to do is you have to position this square in this corner. So it has to be in the bottom right corner, not bottom left as it currently is. And try to make it so that when I change the screen width and screen height, it will still be at the bottom right corner. Which means that this 150 and 150 and 00, those magic values, as they're called, should not be magic values. It should be calculated from screen width and screen height. Finally, you can see that in the loop we are also changing the camera modes, and we can see that this is done every 3 seconds. So once it's 0, then it's 1 and 2. So currently it's also changing, but since the modes 2 and 0 don't do anything, this is like not overwritten. So this is just stays like this. But for example, if I do this and do I don't know 10, and then I run, can see that I had to wait for a bit, but that looks like it does not change. Okay. Oh yeah. So for example, if I change this to 10 and I run it, then the camera position has changed. So if we look at this corner one, yeah, now it changed. So we can see the floor here for 3 seconds or 6 seconds. And when it changed back here, then this is used. So you guys have to change this these values here to be in different position, and the up vector has to change as well. And yeah, do not forget to answer this question: what happens if the field of view is too big or too small? And what's really useful for this is this chapter here, where we are talking about the perspective projection, and look closer to this matrix here. You can see that the aspect ratio is used here as well, but what's more important is the alpha, which is the field of view. Alpha is the field of view. So what changes if alpha is too big or too small? So you can use this matrix here to construct your explanation. Yeah, that's it for the projected chopper. If you have answered the question in the text box and submitted, then that should be it.